Hello, my name is Mr. Petit, and what I want to do is I want to go through a conductivity problem to help those of you that may have missed this week's lesson and how you solve for conductivity and the amount of energy that can be transferred when we have a situation where a room is warm and maybe the outside is colder, and we're trying to see how much heat is being lost through a window or something to that effect. First thing we have to do is we have to take a look at our problem here and go ahead and look at that. And we're going to write some things down here as soon as we go. But anyway, what we have here is we want to know how much heat is transferred through a window that is made of glass. So our window is up here, and it's a 1 by 1 meter window with a thickness of 0.005 meters. So a fairly thin pane of glass that this window is made out of. The inside air temperature is 23 degrees and the outside is 10 degrees. So right away, I know that my temperature inside is much higher than outside. So thermal energy will then travel through this pane of glass to the outside. We want to know how much of that energy is actually transferred out. So that's Q right there. So our question mark is, can we solve for Q, which is the amount of energy that's flowing through this window? So we have a formula over here that we use to figure out how much energy is conducted, and this is the formula that we use. Now, one thing is this formula typically is done over time, so how much energy is happening per second, let's say. But what we want to do is we want to see how much energy is transferred through the course of 1 minute. So that is one thing that the problem I'll add here. So 1 minute is also what we want to know is how much energy is transferred during that time. In order to do that, we got to make sure that time moves over to the other side of this equation. So I'm just going to make an adjustment here. I'm going to multiply both sides by t. And so now these t's cancel out. So we know that Q is this formula times t, and we'll get to that here in just a second. So this is our formula, and we're going to plug in the different values that we have up here that we can identify. The first thing we have to identify is K. Well, the substance that we're using, it says in the problem, it says that we're using glass. So with glass, we're going to highlight this right here, and this is our K value up here. The K value is different for different substances. In this case, K for glass is 0.8, so we know that's our K. Now that we know K, we go to our next variable, which is A, the area. The area, like I said before, is 1 meter squared, so we have that value, and that's the area in which the heat is traveling through. We also then need to figure out our temperature difference, which is delta T. In order to do that, we subtract the high temperature by the low temperature, so we take the 23 degrees Celsius and we subtract 10 degrees Celsius, and that gives us 13 degrees Celsius. And so that is our change in temperature, or the difference between the two temperatures is 13 degrees Celsius. Now that we have that, our next variable is the distance or the thickness, or how far the heat is traveling. In this case, the window is very thin, so that's 0.005. And again, we're going to look at how much heat would be transferred over the course of a minute once we solve our once we plug in our variables. So let's go ahead and do that. So we're going to write down Q, and this could be also written down in your notebook, your chill, but Q equals K, which we already said is 0.8. We're going to multiply that by A, which is 1 meter squared, times delta T, which is 13. And we're going to divide that all by our distance, which is 0.005. I'm not putting all the units down here, so it's a little easier to see, but basically the unit that it's going to end up being is joules, and joules is what we give for heat energy. That is the unit for heat energy. It says we're going to do this for a minute. Remember, we added that to the problem, so we're going to multiply. Once we get this answer, we're going to multiply this answer times 60 seconds. So that's what constant is in seconds. So we got to use that when we multiply by 60. Again, that's the 1 minute part. So I'm going to take my calculator and I'm going to just use my, make sure that you hit equals when you do your operation. So I'm going to hit 0.8 times 1, which we know is just 0.8. And we're going to multiply that by 13, and we get 10.4. Now I'm going to divide that by 0.005, and I basically get 2,000 2,080 joules. And I'm going to multiply that by 60 to see how much energy that would be in a minute. And that's going to be a big number. And so that's going to be 124,800 joules, and that would be for 1 minute. So that's how much heat energy would be released from the inside during that time. And that's why we have to keep, our furnace running and things like that, because our buildings are always losing this heat energy. Now, look at what would happen if we changed the material. If we changed it to wood and we basically said, you know what, I don't want to look out this glass window, we would change K. Now, K is a much lower value. That would decrease Q. So that would decrease the amount of energy lost, and that makes sense. Styrofoam would be even better. It would even lower the Q even more. So those things would cause the energy levels to drop in terms of how much we're losing. If we said we wanted to make instead of using glass, we wanted to use just steel, notice that we would lose more energy because our K value goes up. So this value can cause changes. The other variables can affect it as well too. So let's take a look at how we would apply this to the hot soup problems that you have to solve for. In this case here, we have an example of a hot soup problem. We have a pot of soup that is 100 degrees, and our hand is around 37 degrees Celsius. Now the area changes quite a bit because now we're dealing with a different object. We're not dealing with a window, where instead we're dealing with a spoon, which is longer, so the distance goes up. That would affect how much energy would travel. Again, that's going to reduce the amount of energy that's being transmitted through that spoon. Notice that the area is much smaller too. That surface area that it's traveling through is a much smaller amount here that it's traveling through through that spoon. So that's going to be a little bit different as well. Now the spoon could be made of different materials as well. It could be made out of glass, wood, steel, spoons and all those different things. And so what you need to do is you need to compare those two different things to prove you understand, which one's going to transmit more heat in this case here. So you can use this. This is sort of a setup just to show you what you're going to do. But again, it's the same thing. Our Q we would be solving for, and in this case, Q equals, our K value. Let's say that this spoon was made out of wood. Well, then we would let's choose that one. That would be 0.15. So we have the 0.15 is our K value. Let's multiply that by our area, which is a really small number, the 0.000009. And then we're going to multiply that by our temperature difference. In this case, it's 100 minus 37, which would be 63 degrees. So that 100 minus 37 again is our temperature difference. So that's the difference in temperature there. So again, 63 degrees would be that. So it's a bigger temperature difference in this case. But again, we know that soup is hot. That's boiling right there. And then we divide that by our distance. So our distance would be D equals 0.1 meters. And so we can solve this. And now we're going to just solve this for 1 second, like in terms of how fast this heat is moving. So let's see what we get. And maybe we'll multiply by 60 seconds too to see what that would be. So it's a 0.15 times 0.000009 equals, that's a small number, and I'm going to multiply that by 63. And then I'm going to divide by 0.1. And so I get a very, very small number, and it probably should be put in scientific notation. And so we'll show you that. That number is going to be 0.000 0.85 joules. That's what we get for our Q. Now, the proper way to do that is put in scientific notation, and that would be to move your decimal 1, 2, 3, 4 places. So I just made that number bigger. So that means I have a small exponent. So that would be 8.5 times 10 to the negative 4. And that would be joules. So Q equals that. And so that's how you solve for Q for a spoon problem. And again, we could multiply this by 60 to see how much energy was transferred in 60 seconds if we wanted to. You just have to multiply that. So give those hot spoon problems a shot and get those submitted. And if you have any questions, let me know. Thank you.